Can it seem that we are seeing it on the other way around?
So, welcome to today's live session. Today, it's a very special day to have our partner from Observatory du Sahara et du Sahel, OSS Tunisia. We have Mr. Anis, who will be talking about some of the amazing work on soil organic carbon. And we've been supporting him with Edward and Joseph. Maybe Edward and Joseph can say something and welcome Anis. Thank you.
I can. I honestly team. My pleasure to be part of this presentation. Thank you.
Hello, everyone. Hello, Anis. It's great to be part of this presentation and see how the work that 2SS has been doing. And right, I want to display it today on the live session. Thank you, Ken.
Thank you so much, colleagues. Over to Mr. Anis to present to us, and next week he'll be back. Very good session in French and English, respectively. Welcome. Bienvenue.
Thank you, Ken. Thank you to everyone. Today, though, so we will start by presenting our first sub-indicator related to the soil organic carbon monitoring. This live sessions will show a presentation about a brief presentation about the soil organic carbon elements, components, and also the developed notebook that we did. So if we start, so our first sub-indicator here refers our first sub-indicators here refers to the organic constituents in the soil, including the decomposite plant, animal residues, soil organisms, and substance synthesized by soil microbes. So, the soil organic carbon here, or the organic carbon here, plays a critical or vital role in maintaining soil health, enhancing nutrients, and contributing to carbon sequestration in terrestrial ecosystems. So this sub-indicator is really important in terms of soil fertility, water retention, biodiversity, and climate regulation by storing atmospheric carbon, and also this is a key indicator for, as I say, the soil health, and also the to know or to have more information about the soil capacity to support life. So as this illustration presents, so in the soil organic, so we have many level here, many level or depth, if you can see, to study to develop services or tools about. So this is an example here. We have a different depth. Depth could be could attempt 50 centimeter of depth, maybe 30 centimeter, 20 centimeters, etc. So this element, the soil carbon, is really play a role in the global carbon cycle by both storing and releasing the carbon, and it interacts the dioxide also of the carbon dioxide, and it interacts dynamically with the atmosphere and biosphere and also the hydrosphere components. So for the carbon cycle, we have the different parts that include that do part of the carbon cycle. So we have if we can start with the decay organisms, the dead organisms and waste products, the root respiration in order to adapt to the carbon dioxide, and then to the photosynthesis are as last part or last phase of this cycle. So Why this soil organic carbon is really important? So this element could improve the soil fertility and could play a key indicator to have to share with us um, an idea about the soil fertility and structure to increase also this soil's water retention capacity. And soil organic carbon promote also the biodiversity and microbial biodiversity, mitigating the climate change by sequestrating carbon, and also this element contribute to the food security and ecosystem resilience as part of the fifth SDGs indicator. So in the context of a land degradation and more specifically in the SDG 15.3.1 indicator, so this element is really aims to combat the desertification by and restore degraded and land and also soil by including land affected by desertification, drought, and floods, and strive to achieve a land degradation neutral world by 2030. So, the soil organic carbon in the context of land degradation is one of three sub-indicators, which are the land productivity, land use land cover, and also the soil organic carbon. So then, these three sub-indicators are mentioned here with details. So based on the SDG 15.3.1, which is defined as the proportion of degraded land relative to total land area, and is assessed using the three mentioned K sub-indicators, which for the land productivity, which measures the biological productive capacity of land, and land use land cover, which analyze the changes in the land use and land cover classes, and also the soil organic carbon, which assess the changes in the soil organic carbon stocks in the area of study. And to define the soil organic carbon, or to estimate this sub-indicator, we need to define the baseline values using the ISDA soil for our case, which is a data with a 30-meter of spatial resolution showing the spatial distribution of the carbon stocks data for the top of 30 centimeter of the soil profile. And then we used also the reclassification of the land cover maps into 7 classes, which are the forest, grasslands, croplands, wetlands, artificial areas, paylands, and also the water bodies. And finally, the estimation of the changes in carbon stock by applying carbon conversion coefficients based on the land use land cover, the changes to the management practices and inputs in accordance with the guidelines of the UNCCD and other references. So this is an overview about the methods that we used for our method. So this so we started with initial soil organic carbon based on the conversion, based on the land cover series, and this series is converted to values or classes based on the C stocks distribution in last 20 years, and then by using a matrix and a factor called F, which is related to the climate regions indices or values, and this ones will help to have an idea about the changes in the carbon stocks, and finally based on two periods of time range of study, which are the target period and the baseline period. So based on this, we could calculate or compute or estimate the degradation classes, the carbon stocks changes here from using the baseline period and the target period. So as final classes, we will have degrading, stable, or improving classes. And to do this, we need to do to follow a lot some steps to do this, which are the data selection and preparation. So here we need to use or to call some data from the Digital Africa production products to use it later in this notebook. And this data are basically the ESA CCI with 300 of meter of spatial resolutions. There is the soil and also the climate regions data to be integrated later when we'll use the we will use a matrix for the C or the carbon conversion factors. Then the soil classification and reclassification, which is based on the soil data. The calculating of carbon stocks by depth. Here, for this example, we use the 30 centimeter of depth, and then the analysis of land use land cover transition and carbon change. This is to will help to do a connection between the ISDA soil and the land use land cover, because as we can see here for the case of the South Africa production products, we have only one data for ISDA soil, which is the 2001 for the relevant to the year 2001. Then finally, we do the mapping and the visualization of results based on the results what we obtained, um, which are based on the soil organic carbon for the target period and the soil organic carbon for the baseline period. So we will do a computing based on a formula that we will see later during this presentation. So some of results that we have obtained based on the different computing that we did. So we have obtained some maps and also the matrices, and also some statistics relevant to the different parts of this notebook. So if we can move to the notebook. So Ken, sorry, Ken?
Yes, Anis.
Yeah. Joseph,
This is Joseph.
is this the notebook? Are you showing this notebook? Is it okay?
Yes, I was seeing from the city one. Maybe you can zoom in a little bit for to see.
Okay, I will do. So I think it's.
It's okay from my
Is it
end.
okay?
It's okay. Thank you.
Okay, thank you. So here for the soil organic carbon notebook developed in collaboration with the South Africa. So this notebook presents a tool that could help users to better estimate the spatial distribution of the soil organic of the carbon organic in the area that this user could select it. So for this part, we use it so after installing the different libraries and calling the different and importing the different libraries. So we used a polygon as GeoJSON file here to uh, to make things more easier. So for the user, is for him, it's only he needs um, to upload the GeoJSON file here, and of course with the climate region file, GeoJSON file also, and then he ran the notebook, and automatically he will receive the results later. So just let me start explaining this. So for this notebook, we after importing or uploading the GeoJSON files relevant to these sub-indicators, we initialized the data cube, and then doing some calculation here to convert the data, because here we have special data relevant to the organic carbon. The for this So for this part, we did a call for the data for the carbon organic, which is represented into two depth here. The first is from 0 to 20 centimeter of depth. The second one is from 20 to 50 centimeter of depth. So then, to do this, to do the calculation of the soil organic carbon distribution at 30 centimeter of depth, so we did some, we used this formula to calculate and to extract the data at this level, means at 30 centimeter. So then we visualized the data results in this area. So for this case, we used the area of Sidi Bouzid, which is a region in central region of Tunisia. So this this notebook so will be basically using this this limit or this area of study to monitor the spatial distribution of the carbon organic at this at 30 centimeter of scale. So after extracting the data, after computing the data at this scale, so then we loaded the ESA CCI for the range, the time range from from 2000 till 2019. So first we selected the baseline period from 2000 to 2013, and the target period from 2014 to 2019. So for this part, so we selected or we created a new folder for the different results that we will have later. Then we colored the different, we loaded the different data sets and the masks relevant to the land use land cover relevant to the ESA CCI. After that, we did a mask to the area of interest, as I said, which is related to the GeoJSON file polygon, and then we plotted the data into two maps that shows the two periods, which is the first, as I mentioned, as I said, the baseline period from 2000 to 2013, and the second one, as I said, from 2014 to 2019. Then we reclassified this data, the data related to the ESA CCI, and into, as I said, as I mentioned in my in the presentation. So we classified this into forest, grassland, cropland, wetlands, artificial classes, and bare land, and water bodies. Then we visualized this two maps relevant to these two periods with the different classes as you are seeing here. After that, we created a land use transition matrix. So this transition matrix is will help after this to have an idea about the changes into this for this periods. It means from 2000 from the baseline period and the target period. And then in order to have an idea, in order to have a land use land cover changes maps with 3 classes. So as a result, we have this map, and this map represents or show the different changes into the 2 selected periods. And here we can see that we have 3 classes here. The first is the area that is more than 80% of this area is a stable class, but we have also another ones like the degrading classes, which is basically or mainly on the eastern parts and northern parts, and an improving is visualized here, especially is mentioned, sorry, especially in the southern part. Then a statistical visualization. Then a land use land cover, this spatial distribution here showing the that more than 97% is a stable class, and more than 2% is a degrading, and also 0.3% is an improving area. After that, we did a transition matrix here to show the changes relevant to the land cover between the baseline and the target periods. So this matrix will help to have an idea about the changes based on the if you can see, it translates the changes between different land use land cover classes. So after this, we included into this matrix, we included a conversion coefficient, call it F. This conversion coefficient will help to translate the land use land cover classes obtained from or between the baseline period and the target period to a spatial carbon organic distribution into the area of CDWZ here. So to do this, we included the for each value here related to, for example, the cross between the 2 classes, for example, artificial areas and also the wetlands, for example. Here, we add a value relevant to these changes in order to connect the area or the this information relevant to the land use land cover change classes with the climate region classes. So to do this, we uploaded the JSON file relevant to the climate region distribution at the same area. Then we extracted the F or this coefficient, which is relevant to the carbon conversion. We extracted this from this data, and then we multiplied it by the we used this in order to extract the information relevant to the carbon conversion based on the spatial distribution of land use land cover and the climate change, and also across with the soil with the carbon organic soil distribution. So this map here presents or shows the carbon conversion based on this matrix and based on the 3 sub indicators for the soil organic carbon. And then we estimated targets, the target year here. We estimated the soil organic carbon concentration for the target year, and then we do the same thing for the baseline period. As a result, we obtained two maps here. First is related to the baseline soil organic carbon concentration, as you can see here. This show the concentration, as I said, for the area of study at the period from 2002 and 2013. And the second one, which is relevant to the target period here, which is relevant to the soil organic carbon concentration for the target period. And this is to show the carbon organic concentration from 2014 to 2019, which is the selected the target period selected for this case. So then we calculated the soil organic carbon percentage change here from 2014 to 2019 based on these two maps. So here we used a formula that shows the this distribution in order to have a classification later for three classes here about to show the changes of the soil organic carbon from for the target period. So for this we have as a final results for the soil organic carbon three classes, and improving classes which is mainly on the south, and also the degrading classes also in the south mainly for this region, and a stable class which is, as you can see here, occupying the wall, if you can see, areas of Sidi Bouzid, of our region of study. So this is the final map that show these changes of soil organic carbon, always as I said, based on a formula. This formula is based on the calculation of the differences between the soil organic carbon in the for the target period and the soil organic carbon for the baseline period divided by the soil organic carbon obtained for the baseline period. So as you can see, after that, we have a section for the statistics that could help the user to better understand these changes based on the calculated, or based on this soil organic carbon change classification map. So as we can see here, this map show us that more than 99% is a stable class, with 0. almost 3% it's related to the degrading classes, and finally the improving classes, which is also with 0 to 26% of improving classes. So this part really is really important to guide the user, to give him an idea about what is the soil organic carbon and how are the different changes for the selected period. So for the user, we can change the selected, of course, target period, and also the baseline period. So it depends on his study, and it depends also of his area of study. So this was our developed part for soil organic carbon. And as the final part here, the user will receive the results automatically in the results folder with different format. So here we will have a PNG format and also TIFF format. So the user can help can use this data for in any other how can I say, for example, softwares, or to valorize it into another subjects. So this tool is really important. This service is really important, and we think that this this sub-indicator, with crossing it with other sub-indicators that we are that they are under developing, like land use, land cover, and also the land productivity. These three sub-indicators will help effectively, especially with the with using with automatic computing like this, will help to better estimate the land degradation, and as I said, with if we can say it's a swift, or we can extract rapidly the land degradation statue for any region in just few minutes. So this is the our first sub-indicator that we have that we developed, and we are, as I said, working on the next sub-indicators, which are land productivity and the land use, land cover, in order to make things more easier, and in terms of land degradation for the users, and also to make the Digital South Africa services always as one of the important services for in terms of climate change, and also for land degradation parts. So thank you, Joseph. I think that for this presentation, as I said, this is really Digital South Africa plays a crucial roles in terms of as a powerful, is a powerful and accessible Earth observation service. As I mentioned here, soil organic carbon monitoring is really one of these powerful tools that can help users at different scales, like national, like regional, and also local, as we can see. And by leveraging this high resolution data, so also with an open source platforms, I think that this really helpful to the users to enable the timely, accurate, and cost-effective assessments for soil organic carbon stock. So these tools, or the other tools that they are under developing, will support surely for an informed decision making and land management, climate change mitigation, as I said, and sustainable developing. Thank you, Edward. Thank you, Joseph and Ken, and over to you.
Thank you so much, Anis, for today's presentation, and just giving a highlight of the presentation on soil organic carbon, and also adding to the other continental services that Digital Africa has shared with us, and also sharing some information about our partnership with the GEO, where we've had a series of application areas, and also some of the training courses that we have, including land degradation as well. And also this session was in English. The next week we'll have the same session in French, and also acknowledgements of the partners, especially Hamzi Trust and Australian government, and other partners, especially OSS, Observatory du Sahel et du Sahel. And also thanking everyone for joining us in today's live session, and also acknowledging the partners who've joined us, especially Ali from Zanzibar Environmental Management Authority, who was a student of State University of Zanzibar, Ali, are you able to share with us?
Yeah, I'm here listening to the meeting here and Victoria, very beautiful, very well, and we get a lot of information and techniques to solve some problems facing Zanzibar here, as well as in Zanzibar Environmental Management Authority here, we used to do some environmental monitoring like coastline monitoring. So Digital Earth Africa has helped us very much, and we still use it in some projects as well. But right now, as you see, we have some technical challenges to our sandbox as it's continuing to be solved. And I think, inshallah, after a few weeks, maybe we can get it. Thank you.
Inshallah, Ali, we are working on it and providing alternative access. So also acknowledging other partners, we have CAC, we have Fatu, if she's there. Also, we have other partners, just recognizing them for joining us, especially Andile from the South Africa Radio and Astronomy, who is a champion and a supporter of the Big Data School. Andile, greetings from South Africa.
Thank you so much, Kenneth. Thank you so much to all the partners. It's always warm to hear what other colleagues are working on the different parts of Africa. It's quite interesting to find out and to notice that remote sensing and Earth observation is a universal language that all in Africa and the rest of the world we are conversant in. Thank you so much, and thank you so much for the presentation.
Thank you so much, Andile, and representing South Africa as part of the G20. I can see things are going very well under the presidency of South Africa. Thank you so much. So thank you everybody for joining us for today's session. Next week it will be in French, and also just pausing for any other question. Thank you so much.